The world you see isn't real. Not in the way you think it is, anyway. The chair you're sitting on, the screen you're reading, the air you're breathing. It all feels solid, predictable. It follows rules. If you drop a ball, it falls. If you push something, it moves. This is the world our brains were built to understand. It's a world of cause and effect, of definite positions and reliable outcomes. Let's call it the classical world. It's the world of common sense. But underneath it all, at a level so small you can't even imagine it, there's another world. A world with a completely different set of rules. This is the quantum world. And the rules there are not just different. They are bizarre. They defy every piece of common sense we have. They sound like something from a fantasy novel. The quantum world isn't weird on its own terms, it's just doing its thing. It's weird to us. It's weird because our brains, our language, and our intuition are all tools designed for the big classical world. When we try to use those tools to understand the quantum realm, they break. The weirdness we feel is the sound of our intuition snapping. It's the friction between the reality of the universe and the simplified model of reality that we carry around in our heads. So, why is it so weird? The answer isn't a single thing. It's a whole collection of things that, taken together, paint a picture of reality that is fundamentally probabilistic, interconnected, and downright spooky. Let's start with the most basic building block of our confusion. In our world, things are either one thing or another. A light switch is either on or off. A coin toss is either heads or tails. You are either in the kitchen or in the living room. You can't be in both. This seems like an obvious, undeniable truth. But in the quantum world, this isn't true. A particle, like an electron, can be in multiple places at once. It can be spinning clockwise and counterclockwise at the same time. It can be a particle and a wave at the same time. This state of being in multiple states at once is called superposition. Think of it like a spinning coin. While it's in the air spinning, it's not heads and it's not tails. It's a blur of both possibilities. Only when it lands and you look at it does it choose a side. Quantum particles are like that spinning coin, but all the time. They exist in a cloud of possibilities. An electron orbiting an atom isn't a neat little planet going around a sun. It's a smear of probability, a cloud where the electron is more likely to be here than there, but it is, in a very real sense, in all those places at once. This isn't just a philosophical idea. It has real, measurable consequences. The most famous demonstration is the double slit experiment. It's simple, but it breaks our brains every time. Imagine a wall with two vertical slits in it. You stand on one side and shoot something at it, say paintballs. On the other side is a back wall that will record where the paintballs hit. If you close one slit and fire, you'll get a single band of paint on the back wall, right behind the open slit. If you close the other slit and open the first one, you get a band behind that slit. Makes sense. Now, if you open both slits, what do you expect? You'd expect two bands of paint, one behind each slit. Simple. Common sense. Now, let's do the same experiment with something quantum, like electrons. Fire them one at a time. If you only have one slit open, you get what you expect, a single band on the back wall where the electrons have hit. But when you open both slits, something impossible happens. You don't get two bands. You get many bands. It's an interference pattern. This pattern is something you only see with waves. Imagine dropping two pebbles into a pond. The ripples from each pebble spread out. Where the crest of one wave meets the crest of another, they make a bigger wave. Where a crest meets a trough, they cancel each other out. This creates a pattern of high and low water, an interference pattern. The electrons are creating this exact pattern on the back wall. This means that each single electron, fired one at a time, is behaving like a wave. It's going through both slits at the same time, interfering with itself, and then hitting the back wall. Think about that. A single object is in two places at once. That's superposition in action. It's not a particle. It's not a wave. It's something else that acts like a wave when you're not looking, and a particle when you are. But here is where it gets truly strange. The physicists who first saw this were baffled. They thought, okay, let's see which slit the electron is really going through. So they put a little detector by the slits, a sort of tiny camera that would tell them this electron went through the left slit or this electron went through the right slit. They turned on their detectors and ran the experiment again, and the interference pattern vanished. The moment they observed which slit the electron went through, the electron stopped acting like a wave. It started acting like a paintball. It went through one slit or the other, and it produced two simple bands on the back wall, just as common sense would predict. The very act of looking, of measuring, forced the electron to make a choice. It was as if the electron knew it was being watched. The spinning coin was forced to land. The cloud of possibility collapsed into a single, definite reality. This is called the observer effect, or more accurately, the measurement problem. The universe seems to behave differently when we're not looking at it. What we think of as passive observation is actually an active participation in creating reality. This leads to a deep, unsettling question. What counts as an observation? Does it have to be a conscious human? A scientist in a lab coat, or is a simple inanimate detector enough? The consensus is that any interaction with the wider environment is enough to force a quantum system out of superposition. A stray photon bouncing off the electron is enough to measure it and collapse its wave of possibilities. But this doesn't make it any less weird. It just pushes the weirdness back a step. It means that reality is constantly being decided, moment by moment, by interactions. So, that's one pillar of quantum weirdness. Things don't have definite properties until you measure them. They are just a haze of potential. The next pillar is something called quantum tunneling. In our classical world, if you throw a ball at a wall, it will either bounce off, or if you throw it hard enough, break through. It will never, ever just appear on the other side of the wall without damaging it. A wall is a barrier. You need enough energy to overcome it. In the quantum world, that's not true. A particle can spontaneously appear on the other side of a barrier. It shouldn't have enough energy to cross. It's like a ghost walking through a solid wall. This is quantum tunneling. How does this work? It goes back to the idea of particles as waves of probability. The wave doesn't just stop dead at the barrier. It fades away, getting smaller and smaller as it goes into the wall, but for a very thin barrier, the wave doesn't fade to zero before it reaches the other side. There is a tiny, but non-zero, part of the wave that makes it through. Since the wave represents the probability of finding the particle, this means there is a tiny, but real, chance that the particle will simply pop into existence on the other side of the wall. It didn't break through, it tunneled. This isn't just a quirky theoretical idea. It's happening all the time. The sun wouldn't shine without it. The core of the sun is a fusion reactor, smashing hydrogen atoms together to make helium and release energy. But the sun's core isn't actually hot enough for this to happen, according to classical physics. The protons, which are positively charged, should repel each other too strongly to ever get close enough to fuse. They don't have enough energy to overcome that barrier, but they do. They cheat. They use quantum tunneling to get through the repulsive barrier and fuse together. Every ray of sunshine that warms your face is a product of this impossible-seeming quantum trick. Modern electronics also depend on it. The flash memory in your phone and computer uses quantum tunneling to trap and release electrons, which is how it stores data. So this weirdness is not only real, it's useful. So we have superposition and we have tunneling. But the weirdness doesn't stop there. Perhaps the most mind-bending concept of all is quantum entanglement. Is Albert Einstein, who was deeply uncomfortable with quantum mechanics, famously called it spooky action at a distance. Entanglement is a special connection that can exist between two or more particles. When particles are entangled, they are linked in a way that their fates are tied together, no matter how far apart they are. They become part of a single system, not two separate objects. Let's use an analogy. Imagine you have a pair of magic gloves. One is a right-handed glove and one is a left-handed glove. You put them into two separate boxes without looking, and you give one box to your friend. Your friend then travels to the other side of the galaxy. At an agreed-upon time, you both open your boxes. The moment you open your box and see a right-handed glove, you instantly know with 100% certainty that your friend has a left-handed glove. Now, that doesn't seem so spooky. You might say, of course you know. The handedness of the gloves was determined from the start. One was always right, and one was always left. You just didn't know which was which until you looked. This is the classical common sense explanation. The information was just hidden. But that's not how entanglement works. In the quantum version, the particles are like the spinning coin from before. They don't have a definite state until they are measured. Let's say we entangle two electrons so that their spin will always be opposite. Spin is a quantum property, but we can think of it as being either up or down. While they are entangled, neither electron has a definite spin. Each one is in a superposition of both up and down. They are both spinning coins. Now, you take one electron, and your friend takes the other to the other side of the galaxy. You measure the spin of your electron. The moment you measure it, its spinning coin state collapses and it chooses a spin. Let's say it becomes spin up. Instantly, at that very moment, the other electron, light years away, becomes spin down. There is no time delay. It happens faster than the speed of light. This is the spooky part. How did the second electron know that the first one had been measured? How did it know to become spin down? They seem to be communicating, but Einstein's theory of relativity says that nothing, not even information, can travel faster than light. For decades, physicists debated this. Einstein and others thought there must be hidden variables, just like with the gloves. They argued that the electrons must have had their spins decided from the moment they were created, and we just didn't know them. Quantum mechanics, they felt, was incomplete. But in the 1960s, a physicist named John Bell came up with a mathematical test, now called Bell's theorem, that could actually distinguish between the hidden variables idea and the spooky action of quantum mechanics. It was a test that could be performed in a lab, and over the last few decades, the experiment has been done many, many times with increasing precision. The results are in. Quantum mechanics was right. Einstein was wrong. There are no hidden variables. The universe is genuinely spooky. The two electrons are one system, and a measurement on one part of the system instantly affects the other part, regardless of distance. This shatters our deeply held belief in locality, the idea that an object is only directly influenced by its immediate surroundings. Entanglement shows us that the universe is interconnected in a way that we can't see and don't have the intuition for. It's not just a collection of separate objects, it's a web of relationships. So, why is all of this so weird? It comes down to a few core clashes with our classical worldview. First, there's the death of determinism. Before quantum mechanics, the scientific dream, starting with Isaac Newton, was of a clockwork universe. The idea was that if you could know the precise position and momentum of every particle in the universe at one moment, you could, in principle, calculate the entire future and the entire past. The universe was a great machine, unfolding according to fixed, predictable laws. Your life, the history of the world, it was all predetermined from the Big Bang. Quantum mechanics destroys this dream. At its very heart, the universe is not deterministic, it is probabilistic. You can never know with certainty what an electron will do next, you can only calculate the odds. You can say there is a 30% chance it will be here, and a 70% chance it will be there. And that's it. That's all the information there is to know. The randomness isn't because of our ignorance. It seems to be a fundamental feature of reality itself. When you measure the electron's position, it's not that you're discovering where it was. You are, in a sense, participating in the role of the cosmic dice that determines where it is. This is a profound shift in how we see the world, from a predictable machine to a game of chance. Second, our language fails us. We try to describe quantum objects using words from our everyday experience. We say an electron is a particle, but it also behaves like a wave. So which is it? It's neither. It is a quantum thing, a wavicle perhaps, that has properties of both, but is fully neither. Our language is built on categories that exist in the macroscopic world. A thing is either here or there. It is a wave or a particle. It's on or off. By forcing quantum reality into these clumsy classical boxes, we create paradoxes. The weirdness is partly a linguistic problem. We don't have the right words because we don't have the right experience. Third, our brains are simply not wired for it. Human intuition is a powerful survival tool that has been honed by millions of years of evolution. It's great for figuring out the arc of a thrown spear, the speed of a charging lion, or the stability of a pile of rocks. All of these things are large, slow, and predictable. They are classical objects. We have zero evolutionary experience with superposition or entanglement. An animal that saw a lion as a probability cloud of being both behind the tree and in front of the tree would not have survived for very long. We evolved to collapse the wave function instantly, to see a definite world of solid objects, because, at our scale, that's what we need to do. Our common sense is a user interface for reality, a simplified operating system. Quantum mechanics is the underlying code, and looking at the code is always more complex and confusing than using the simple graphical interface. This leads to a final, crucial question. If the world at its base is so weird and probabilistic, why does our everyday world seem so normal and predictable? Why don't we see cats that are both asleep and awake, or cars that tunnel through garage doors? The answer has to do with scale and a process called quantum decoherence. A single electron can be kept in a delicate state of superposition, isolated from the rest of the world in a careful lab experiment. But a cat is not a single electron. A cat is made of trillions upon trillions of atoms. Each one of those atoms is a tiny quantum system, but they are all interacting with each other. They are bumping into air molecules, absorbing and emitting photons of light, and being jiggled around by heat. Each one of these tiny interactions is a measurement. Each time an air molecule bounces off the cat, it checks where the cat's atoms are. This constant, relentless measurement by the environment destroys the fragile quantum superpositions almost instantly. The countless possibilities of the cat's quantum state are forced to collapse into one single classical reality. This process is called decoherence. It happens so fast and so thoroughly for any object large enough for us to see that we only ever experience one definite outcome. The classical world of common sense is not the fundamental reality, it's an emergent property. It's what happens when quantum weirdness gets averaged out over huge numbers of particles. It's a high-level summary. The solidity of a rock is an illusion created by the statistical behavior of a staggering number of quantum particles, all constantly interacting and collapsing each other's possibilities. So, the quantum world feels weird because it's the real world, and we've spent our entire lives living in a simplified, heavily edited version of it. It's like someone who has only ever seen a pixelated image of a face suddenly being shown the individual cells and nerves and blood vessels that make it up. It's the same face, but the underlying reality is messy, complex, and operates by a different set of rules. It's a humbling realization. It means that our most basic assumptions about reality, that the objects have definite properties, that causes have predictable effects, that things can only be in one place at a time are not universal truths. They are just local bylaws that work well in our particular macroscopic neighborhood of the universe. The weirdness is a message. It's telling us that the universe is bigger, stranger, and more mysterious than our minds are naturally equipped to handle. It's a challenge to our deep-seated need for a simple, intuitive picture of the world. And in that challenge lies its beauty. It forces us to accept that reality is not obligated to make sense to us. We can describe it with mathematics, we can use it to build lasers and computers. But whether we can ever truly intuitively understand it is another question entirely. The weirdness is the gap between the map in our heads and the territory of existence itself. And it's a gap so wide it might just be infinite.